Hey, this is Ken the Metal Professor, and I'm going to go through a couple of fun problems that I interacted with or encountered in a couple of the math subreddits. It's always fun to see problems that have cool stuff in them, especially when you can see a couple of them that kind of follow the same theme. So I'm going to show you two that go remarkably well together that I came across the last couple of days. It's been a couple of days, at least a full day or two since they were posted. So at this point, I think we're out of spoiler territory in terms of just walking through the full solution. I feel like a dork when I introduce myself as Ken the Metal Professor sometimes, but I do these videos and I'm a retired math professor, so there's the professor part. I also do a heavy metal radio show, so there's the metal part, and I also do radio coverage of local independent wrestling events sometimes. So when your YouTube videos in 3 different categories have, up to like 3 or 4 views a piece, you got to maintain that branding. So anyway, let's take a look at a couple of problems involving higher order integration. Starting off with one of them that turns out to be deceptively, is it deceptively nasty or deceptively easy? It looks like it's going to be nasty, and it turns out, if you interpret the question one certain way, that it isn't. So let's take a look. This is multivariable calculus. So if you're in there or have been in there, this should look familiar. If you're still on your way there, maybe check it out anyway just to see what's coming down the road, like a truck at you. So we have a vector field F. It's a flux vector in this particular context. It's got 3 components, x, y, 5x minus 2z. And we're going to build a 3-dimensional surface, which is the graph of this nasty looking exponential function. E to the 36 minus 9x squared minus 4y squared. And we're going to cut that off at z equals 1. So we're going to look at the upper part of that dome. And we are going to use Gauss's theorem, which is also known as the divergence theorem, to calculate a vector surface integral of flux. Okay, so here is a picture, badly drawn, of the scenario so far. So this function, e to the 36 minus some stuff. When x and y are both 0, this is going to be e to the 36. That is a whopper of a value. Okay. Now, as x and y increase in both the positive and negative directions, we're going to be subtracting numbers from that 36, so the z values are going to get lower. And so this is going to be a huge dome, and it's obviously not scaled on this picture. When we get down to the intersection with the plane, z equals 1, we're going to get an elliptical cross section, and that's because when this function intersects z equals 1, in order for e to this stuff to give us a 1, that stuff in the exponent has to be 0, which means it's just the ellipse, 9x squared plus 4y squared equals 36. So there's an elliptical cross section. This flux integral is asking us to calculate the total flux across our surface. Now, this peanut that I've drawn is just a general surface, not the one in particular. When we're looking at flux integrals like that, a surface integral of f dot ds or f dot n ds, we have a vectorized surface, meaning we've assigned orientation vectors, preferably unit vectors, preferably that point outwards. That's designated positive orientation. And this vector field F could represent flux or flow. And so what we're doing is we are going all along the surface and integrating or accumulating all the f dot n's. Now, if n is a unit vector, like this red one right here, and here's the force vector that's applicable at that same location, f dot n is the component of this flux vector in the direction of that normal vector. So what we're doing is we are getting the net accumulated value of flux all over this surface. And when the flux is going inwards, like it is on the left of this made-up diagram, the flux is assigned negative because it's flowing in the direction opposite what the unit vectors are telling us is the positive direction. Over here on the right, where the flux seems to be leaving, that flux is positive, right? Now, what do you know about flow? Unless something weird is going on, the amount of stuff that goes in across this surface has to equal the amount that goes out. Okay? Now, that is under quote-unquote normal circumstances, but still, that's what we are asked to evaluate here, is that net flux integral across the surface. So here's where there's a little bit of ambiguity in the way this question is posed. Let S be the graph of this z equals e to that nasty exponent for z is greater than or equal to 1. The question there is, let me get back here to my picture. Do we want the surface to only be the dome down to where it does hit z equals 1? Or do you want this floor at the plane itself also included as part of the surface? Okay, so those are our two options. An open surface just based on the dome itself down to z equals 1, or a closed surface which includes the dome and also the foot, the basement, in that plane of intersection. That makes a huge difference. The phrasing of the problem, you could take it either way, okay? We're going to assume we want the first way because that one makes it easier, okay? The divergence theorem, or Gauss's theorem, says this: if you have a simple solid region, meaning a simple, it doesn't cross itself, and it's a solid region, so it's a pocket, it's closed off, it's a complete surface, or a complete three-dimensional region, and let S be the boundary of that three-dimensional region, such as the boundary of the peanut there, okay, with outward orientation. That's the geometric setup. There is a vector field in play, which we will likely consider to be flow or flux. It has to have continuous partial derivatives. It turns out that if you're trying to get the surface integral of flux, the net total flux across that surface, you can get the same result by doing a triple integral over a volume of the divergence of that vector field. Okay, so this tells us basically a balance of what's going in versus what's going out. This is accumulating the divergence of the vector field in that same place. Now, there is divergence can be calculated mathematically by just taking your vector field and throwing some derivatives at it, as we'll see. There's a physical meaning for divergence, and it's basically how much space is there in your flow field for flow to be added or absorbed by the medium itself. Okay, so in a particular flow tube, right, so here are streamlines of a flow field. So flow can't go across these black lines. So there's a tube of flow going between them. And let's say we measure the flow or the flux at one point down here on the left, and we measure the flux up here in this larger cross section on the right. If the total flux at point A compared to point B, or cross-section A versus cross-section B, is the same, that means this flow field has no divergence. Divergence is not just spreading out. It's spreading out to make room for more. That's what divergence is, right? If you have a garden hose and it's spraying out water, you just drop it on the ground, the water spreads out on the ground. That's not divergence in a mathematical sense. If you take a hose and put your thumb over the spout and you decrease the space that's there for the water to move through, it speeds up. That's not divergence. Okay, that's just flow as it normally goes. So when the flow across this smaller part is equal to the flow per unit time at this bigger part, there's no extra stuff entering or leaving the medium in between those two locations. And that means the divergence is zero. So if we go back to this picture, if there's no excess flow going into the field or being taken away from the field as it's moving across our peanut, then certainly the net inflow versus outflow has to balance out to zero because what goes in has to be the same as what goes out. So that's what the divergence theorem is telling us. And so back to this problem, if we're assuming that we want the surface to be the entire closed surface, the net balance of flow across and out of the surface all the way around is just the net accumulation of how much divergence there is in the flow field inside that three-dimensional region. Okay, now for this particular vector field, here's the divergence. We throw derivatives at the three terms in the right order, and it's zero. So this is a divergence-free flow field, or incompressible. That's another magic word for it. And so the divergence theorem tells us what physically we ought to understand is that since there's no divergence, what goes into the surface has to be the same as what comes out. Okay, and the divergence theorem settles that out. If we do a triple integral over a volume of the function 0, we're going to get 0 as a result. Okay, if you integrate 0, you get 0. The general hint for this problem is that if you have a scenario like in this problem statement, where was it? This nasty surface and this weird vector field. When you start seeing things that look like they're about to make a super ugly problem, pause for a minute and consider whether maybe it's intentionally deceptively complicated because, like in this case, the answer is going to collapse to 0 without a whole lot of effort, right? They want to make you sweat a little bit. They don't want to make it obvious going into it. Okay, but this answer is 0 if it turns out that we're interpreting this problem to mean we're looking at the fully closed surface. Now, suppose we're not interpreting the problem correctly, and the problem really just wanted us to calculate the surface calculate the flux over the dome down to the plane z equals 1, but we're not considering the flow across the plane at the basement of the surface itself. Well, then what we're going to do is we're going to name our surfaces, the pieces of the surface, S1 for the surface of the dome and S2 for the circular plane down here at the bottom. If the problem is only asking us for the flux across S1, then we could either build that surface integral directly, which would be terrible, or we can still go back to the divergence theorem, but we'd have to understand that there's two different contributions. Okay, if we're only asking for the flux integral over the domed surface, we can still relate it to what we've already calculated, because the full closed surface, S, is just the sum of the dome surface as well as the plane surface. Okay, so the three fluxes would have to add up like this. Now, we've already calculated that this expression on the left has to be 0. This expression here, the flux integral over that flat plane, actually wouldn't be too hard. Now, I'm not going to do it here, but this could be expanded as a regular double integral. You're over an elliptical region on a flat plane, so there's nothing complicated there in terms of it being a surface integral or a double integral. You could get that without too much pain. So this has to be 0 on the left. This piece could be calculated somewhat easily. And so you could figure out what this really, really nasty thing would have to be without having to break it down into its guts. Okay, but like I said, hopefully we are interpreting correctly that we wanted the original take on this, where we want the closed surface all the way around the dome and the base, in which case, because the flow field is incompressible, has a divergence of 0, the net flux integral would also end up being 0. All right, so that was fun. I like talking about divergence. Divergence is one of those things that when I first learned math, I could push the symbols around. I had no idea what it meant. I went out and did some research in a very applied area and came back to teach math afterwards, taught Calc 3, started learning divergence all over again. I was like, oh, so that's what it meant. So it takes a little bit of time for it to percolate. Okay, next problem. This is another one where we have a problem that looks complicated, and it turns out to be complicated, or at least somewhat annoying. It's doable as long as we can put all the pieces together. But it's one where I was hoping something would settle out to 0, but it doesn't look like it does. Okay, find the work done by this force vector field over one loop of r of theta equals sine of 7 theta oriented positively. All right, so here's the picture I accidentally showed before. This is r equals 7 sine theta. We want to do our calculation over one loop, so we'll consider this loop right here in the first quadrant, starting at the origin, sweeping out here and coming back. So we're going to find the work done by a force vector field across that loop. Okay. Now, the way we do work integrals are to parameterize the contour that the force is acting on, and also parameterize with the same parameter the components of the force vector field. The parameter we're going to use is theta, because theta draws the curve for us. So eventually we're going to need the starting and stopping values for theta, but that's fine. The function is sine of 7 theta, so when theta is 0, we're sitting here at the origin. Let's start letting theta increase. Here we go, we're coming out on this loop. When theta gets to pi over 2, that's the maximum that 7 theta is going to be, and that's the maximum that the sine is going to be. So that's where we hit this 1, and then we come back to close off the loop. So we have to decide what theta value is the one where we close off the loop. Well, the sine of some stuff is going to hit 0 when that stuff is 0 and then pi. So if we start at theta equals 0, the next time the stuff that's sitting here is pi, that's when we close out this first loop. So we close the first loop when 7 theta is equal to pi, or when theta is pi over 7. So those are the starting and stopping values of this parameter that's going to drive everything. So here's the scenario from the previous problem that I was hoping would work out that doesn't. If you have a conservative vector field, the work done around a closed contour, like one loop of sine of 7 theta, has to be 0. Okay? Well, this vector field does not have a curl of 0. Maybe it was intended to have a curl of 0, meaning that it would be conservative, but it isn't. This extra third component of 0 was put in there to take our two-dimensional vector field and place it in a three-dimensional universe so we could find its curl. I haven't shown you the curl, but the curl is not 0. Okay, so the vector field isn't conservative, so we cannot say for sure that the work done around that closed loop is going to become 0. We've got to dig for it. All right, so we have to compute our work integral. This is the super duper upgrade of what you learned in 10th grade physics, which is work is force times distance. When you have a constant force and a straight line distance, and then in like Calc 1, you learned how to deal with variable forces but still on a straight line. And now in multivariable calculus, you can have a contour going all over the place, and you can calculate work done by a force that does all sorts of stuff. So this is the super case of doing a work integral. So F is the force vector field. R is going to be a vector curve that tells us about this contour that we're interested in. It's the parameterized representation. dr is right here, is the vector derivative of the vector function that tells us the curve that we're going around. And there's a couple of different uses of r involved in this problem. The bold-faced r is the vector r that draws the curve. Regular old lowercase r is just the polar coordinate, like r equals sine 7 theta. That's the polar coordinate r. All right, so we got to parameterize this curve. The general polar form of this curve is r of theta equals sine 7 theta. As theta sweeps around from 0, the distance from the origin is changing, right? That's how the curve gets drawn. We're going to take theta from 0 to pi over 7. Now, because we're going to need to do a dot product of f dot dr, unless we're going to figure out how to do a dot product in polar coordinates, we need to roll everything back into rectangular form. But we still need to use theta as the parameter. Now, we can build rectangular x and y components of something with x equals r cosine theta, y equals r sine theta. So how does theta dictate x and y? Well, x is r cosine theta. Theta gives us cosine theta. And r is also determined by theta by the function of the curve itself. Okay, so x equals r cosine theta, y equals r sine theta can be opened up into r sine of 7 theta times cosine theta and times sine theta. And now we see how the parameter theta dictates x and y coordinates of the points around this curve. And so we can put all that together in our vector function, which describes the contour. So for this work vector field, we have to load up the vector field f, put its components in terms of theta, and then not just have the vector curve r that we just built, but do dr, which is its derivative. Okay, so first for the vector field, well, it was given originally as negative 10y 6x. Oops, I left that 0 in there, but ignore that. That was a cut and paste error. But because y is r sine theta and x is r cosine theta, we can use those same polar expressions to build out the negative 10y and the 6x. So this horrendous thing here is the parameterized vector field. Okay, these are the two components of our vector function r. Their derivatives require the product rule. The dogs are excited about it. I can hear them barking downstairs. You probably can too. So here's x prime and y prime, and we've put those two together into a really super nasty vector representing dr. Okay, look at all that stuff that's in there. This is gross. And so we need to do f dot dr. So here at the top is f. Here in the middle is dr, and we're going to do their dot product, which means we're going to do the first component of one times the first component of the other, plus the second component of one times the second component of the other. And these, you can see that they're pretty nasty. If you want to pause and look at them a little bit, there are going to be some trig identities that can probably shake these things down a little bit, but this 7 theta versus theta, that's just, that's no fun. Okay. Now, when we add these up to form the dot product, notice that this blob is the same as this blob, right? So these first two terms are going to add together, but the second two are not. Whoops, I got that stupid PDF box at the bottom of my slide. There it goes. Okay, and so it does simplify to this mess. That 10 sine squared theta plus 6 cosine squared theta could change into a 4 sine squared theta plus 1. If we borrowed 6 sine squared theta from the 10, merge that with the 6 cosine theta, and made that 6. Sorry, I was saying that out loud incorrectly. That could change to 4 sine squared theta plus 6, but is that really going to help? I don't know. Okay, but anyway, the final integration that needs to be done for this work integral is 0 to pi over 7 of this mess with respect to theta. Again, if you need to do this by hand, good luck with your trig identities. Okay, I did not do it by hand. I asked Maple for what the value was, and its estimated value is about 1.8. So if you do try this by hand, hopefully you'll get something like 1.8 rounded. Either mine is wrong or yours is. But there it was. 2 crazy examples of vector integration in a higher dimensional setting from multivariable calculus. Now my brain hurts.